Okay, question 5 is the final step of the synthesis, and that is getting this acetal in structure 6 out of the way. We used it to keep those two alcohols from getting in our way when we made the ester. In reality, it's also helpful to keep it out of the way as we do this hydroxylamine side group, but we're not going to cover that yet. We haven't talked about amines yet. And then at the end, we got to get rid of it. So we need to take this off, but we need to do it in such a way that we don't break the ester, which means we have to be a little bit milder. As it turns out, ester cleavage is a little bit more harsh, but we can't just go beat on this with sulfuric acid and water because we're going to lose the ester as well. So the choice here was to use a milder acid, and rather than using water, use ethanol, because then if it tried to approach this ester to cleave it, it would be a little bit harder to do. Apparently works very well. But the point is, yield wasn't reported originally on this, so we don't have numbers to go with it. But the point is, we're not forming the ketone again, we're actually forming a different acetal. So this is a trans-acetalization. We're going from this diol being my acetal to now having an open chain diethyl acetal. So those two ethanols are going to replace these two OR groups that are connected together to make the cyclic acetal here. So let's look at the question as written. Here it is. So essentially that step, the side product from the acetal becomes a different acetal with two ethanol groups attached to it. So we're going to have the two oxygens from this ring displaced one at a time and replaced with the ethanol groups here to give us a different acetal. We don't really care about that, but in terms of the mechanism, it's an easy to remove byproduct, but mechanistically we still kind of need to account for it. So as before, I didn't want you to get messed up with the structure, so I gave you a simpler version. I took out basically everything except for the functional group we care about, just so that we could focus on it. So that's the idea. I want to see how to do it. Now, it is not overly difficult, but it is longer. This is a full acetal mechanism, so this is going to be roughly twice the length of the ones we dealt with in question 3 and 4. There's a lot happening here, because we have to get rid of these one at a time. We can't actually dump them both at once. It doesn't work. So, as before, we're going to have to protonate this to get anywhere near the ability to get rid of it. We need to turn those groups into leaving groups. Now, in a practical sense, because these are chiral and because there are other functional groups in the molecule, that's why the mechanism didn't involve just beating the hell out of it. That's why I said they're using an alcohol. That's why they're using a milder acid instead of sulfuric. Okay, now, much like what we saw with question 3 and 4, we protonate that alcohol. It's a reasonable leaving group. We get rid of it. We're reforming something approximating a carbonyl. Now, we're halfway done as far as the structure goes. We've got one of our alcohols exposed already. And we're basically just getting started here, but getting the other one's a little tougher. So we now have this analog of acetone. We can't get rid of it directly, but what we can do is, as before, form an acetal out of it. So we're going to hit it with a different alcohol, and that's going to loosen it up. That's going to break that pi bond and give us a different acetal than we started with. So this also is an acetal. Still protonated. But it's an acetal. So we're going to need to get rid of that hydrogen. So either the alcohol or another acetal, something's going to take care of that. We could write it a lot of different ways. Probably another molecule of the alcohol would be the best way to write it, but just for simplicity, I'm going to write it as B. Neutral. Very important. We don't have negative charge things floating around in an acidic solution other than the conjugate base, and that doesn't help us. So we have this, and there's our poorly written acetal because I left out the oxygen briefly. So, all right. We still need to make that other alcohol other oxygen into a leaving group. So we're going to have another protonation here. And that's going to involve the other ring-attached oxygen protonating to become a leaving group. So now, one of them is already out. The other one now has a way of getting out. And we have the other acetal, the other oxygen that's already on the acetal. So I'm just going to redraw that so we can start with it at the top of a new page. So we have this already. We have this protonated and cationic. Along with that, we have the dimethyls from the original acetone, and we have our ethyl group for the acetal. As before, very unlikely that we're going to get direct SN2 here. This is a tertiary carbon. Not really any chance you're going to do a direct attack of the other alcohol on this. So we're going to have to go about this internally by making it a carbon into an sp2 carbon. That's the end of the job for getting the alcohol loose. So our actual structure of interest is already free at this point. But just to finish the job, we now have this as the byproduct of that in the presence of more ethanol. So we can get another attack to get the acetal. So we have one that's neutral, we have one that's now protonated, and something is going to act as a base there. Again, probably the molecule of the alcohol, because that is most likely the solvent for this reaction. So here we are. There's the other acetal, and here's our product, which in the case of the original synthesis is the final product. It gets recrystallized after that. So here it is again. That's the removal of the acetal here to the diol here. And then after that, we're just cleaning it up. So it's crystallization after that.